For our next example, we will verify this potential identity both numerically and graphically before performing a partial proof. But first, we need to determine any non-permissible values. Remember that our three instances of non-permissible values in this course are radical functions cannot have negative radicands, that logarithmic functions cannot have arguments which are negative or zero, and in any case where we have a fraction, we cannot divide by zero. A common strategy is to rewrite our identities in terms of cos and sine. Here, we've replaced secant with 1 over cos and tangent with sine over cos. So now we need to determine which values of theta would make cos equal to 0 or sine equal to 0. We know that cosine is 0 where we find an x-coordinate of 0 on the unit circle. This happens at both 90 and 270 degrees. We know that sine is equal to 0 where the y-coordinate is equal to 0 on the unit circle. This happens at 0 and 180 degrees. So we can see that every 90 degrees we're having a denominator of 0 generated in this expression. That means that theta cannot be any multiple of 90 degrees. We write this by saying theta cannot be 90 degrees times n, and then state that n must be an integer number. It's an integer number because we have complete rotations of 90 degrees, and it can be positive or negative, meaning we could rotate in either direction. A numerical verification requires you to substitute the given angle measure in place of theta. Now, we should evaluate each side using exact values. We're going to assume that you have a good understanding of the unit circle at this point and know values such as cos, sine, and tangent for 30, 45, and 60 degree angles. Remember, when we divide by a fraction, that is equivalent to multiplying by its reciprocal. Here we see that both the left and the right side gave 2 divided by the square root of 3. We can confirm that for 30 degrees, both sides of this equation are equivalent. Let's check now when theta is equal to 2/3 pi. You might think of 2/3 pi as 120 degrees and know that the cosine of 120 is negative 1/2. 1 divided by negative 1/2 is negative 2. We anticipate getting the same value on the right side, but take your time just to be sure. Again, when we divide by the fraction, we instead multiply by its reciprocal. We find the same value of negative 2, confirming that this could be an identity. In order to verify this potential identity graphically, we'll simply graph the left side of the equation as y1 and the right side as y2. Remember that since our calculator has no secant button, we'll have to write 1 over cosine x instead. In order to determine a suitable window, use what the question tells you. We know that our domain will be from negative 180 to positive 360. These values will serve as our x-min and x-max. It's not really important what you put as the x-scale here. For the y-min and y-max, it's important to understand that there's no right answer. We've chosen -3 and +3 to give a clear view, but that's based on years of practice. You might choose -10 and +10, and it's no less correct. We see these graphs appear to be the same, and so this is enough to confirm that this could be an identity. We can note that there is an undefined value on y2 where y1 is defined, but this is a matter of non-permissible values and is allowable when discussing identities. Next, we're asked to simplify the expression on the right side of the equation to a single trigonometric expression. Let's assume that it's going to turn into the expression on the left side. That's basically us proving that this is an identity. A common first step is to rewrite all ratios in terms of sine and cosine. So here we've rewritten tangent in terms of sine over cos. Sine over cos divided by sine is like saying divided by sine over 1. And therefore, dividing by sine over 1 is like multiplying by 1 over sine. We see that in this case, sine over sine reduces, and we're left with 1 over cos, which is equivalent to secant theta. This is the same as left side, so we've successfully proven this identity.